Hi and welcome back. So last class we started chapter 12, which is the topic is indefinite integrals, and we did an introduction to indefinite integrals, also known as antiderivatives, and that was in section 12.1. Today we're going to skip ahead to 12.4 and talk about some applications of indefinite integrals. We will go back and talk about 12.2 and 12.3 next class period. Okay, so just as a reminder, in our last class, we talked about this long stretched out s, and then maybe we had a function in the middle, and then a dx at the end. And what this expression says is this expression says, which is an indefinite integral, says find the antiderivative of 4x to the 7th. Another way to say that is to say if the derivative is 4x to the 7, what is the original function? So the way that we did this last time is that if we had the antiderivative of 4x to the 7th dx, then our process was to add 1 to the power, so we have x to the 8th, and then divide the number in front by the new power. So for us, that would be 4 over 8 x to the 8th. And then we have this plus c at the end because we need to add on a constant, because when you take the derivative of a constant is 0, so there might have been a constant that we just don't know about. Okay, so this is a fine final answer, but if I want to, I can clean up this fraction. 4 over 8 can be written as 1/2, so I have 1/2 x to the 8th plus c. Okay, so today we're going to talk about applications of these indefinite integrals. And at least in our first application, what we want to think about is there can be scenarios where we have information about rates of change or how something is changing, like revenue or cost or profit, but maybe we don't know the actual revenue function or the actual cost function. So the scenario that we're talking about today, the application we're talking about today, is what do we do if we know about rates of change, but we don't know about original functions? So we're going to look at an example. So in this example, we are told that the company's marginal cost for a product is MC, which stands for marginal cost, equals 6x plus 60, and marginal revenue is MR, stands for marginal revenue, equals 180 minus 2x. And the last piece of information that we're given is that the company's total cost of producing 10 items is $1,000. Okay, so in this example, we're given a marginal cost and a marginal revenue and this one extra piece of information. So the first question that we are going to ask, and maybe we'll call this part A, the first question that we are asking is, what is the optimal level of production? Okay. All right, so when I read this question, what is the optimal level of production? When I see optimal level of production means the number of units produced and sold. And when we're talking about the optimal level of production, what we mean by optimal level of production is the number of units produced and sold in order to achieve a maximum profit. Okay, so another way to word this question is, how many units should be produced and sold in order to maximize profit? Okay. All right, now this doesn't sound like something that we would necessarily need antiderivatives for, so let's kind of think through this question. Okay, so we want to maximize profit. Now, in chapter 10, I think it was, when we talked about max-min problems, our process was, when we want to maximize profit, step one is to find a profit function, and then we took the derivative of that function and set that derivative equal to 0. All right, so what that would mean is that we would need to come up with a profit function. Now, there's actually kind of a shortcut way of thinking about this question. I want to talk about that shortcut way. Okay, so let's think carefully about that process that we looked at in chapter 10. So our process in chapter 10 to find maximum profit, what we did is that we first found a formula for profit. Okay. And when we came up with our profit formula, we said that P of X is equal to, so profit is revenue minus cost, so P of X is R of X minus C of X. So that was the first step. The second step was to find the derivative. Now, even though I don't have a formula yet, we have profit is equal to revenue minus cost, so symbolically, our derivative, P prime, is equal to the derivative of revenue minus the derivative of cost. And then, after we take our derivative, we set that derivative equal to 0. The reason that we did that in chapter 10 is when we have a profit function, there's a top of a hill, and the slope at the top of the hill is 0. So we want to set our derivative, which describes slope, equal to 0. So 0 equals R prime of X minus C prime of X. Okay, so at that point we would solve for X. Now, something I want to observe here. This 0 equals R prime minus C prime means, well, I can do a little algebra here. I can add C prime to both sides. So when I have 0 equals R prime minus C prime, if I add C prime of X to both sides, I get C prime of X equals R prime of X. C prime, the derivative of cost, is marginal cost. The derivative of revenue is marginal revenue. And so what this says right here is, this says that if we want to maximize profit, we need our marginal cost to be equal to our marginal revenue. So max profit occurs when marginal cost is equal to marginal revenue. All right, so all this thought bubble over here, what comes out in the wash is that if you want to figure out the X value where the maximum profit occurs, then one way to do that is the way that we did in chapter 10, which is find the profit function, find the derivative, set it equal to 0, and solve for X. But an alternative observation is that maximum profit occurs when marginal cost is equal to marginal revenue. So in our example, where we are asked what is the optimal level of production, that optimal level of production occurs, optimal level of production meaning the number of units produced and sold to achieve maximum profit, the optimal level of production occurs when marginal cost is equal to marginal revenue. So in our example, we are told that marginal cost is 6x plus 60, and we are told that marginal revenue is 180 minus 2x. So setting marginal cost equal to marginal revenue, I can solve this equation for x. So some things I can do, I can add 2x to both sides. So I have 8x plus 60 equals 180, and I can subtract 60 from both sides. So I have 8x equals 120, and now I can divide by 8, and I end up with x equals 15. So what this tells me is that the optimal level of production, is for the company to produce and sell 15 units. This level of production, will maximize profit. Okay, so by doing this method, what we've done is we have completely sidestepped coming up with a profit function, taking the derivative, setting the derivative equal to 0, because we were given the information about marginal cost and marginal revenue ahead of time. Okay, so that is part A. Part A asked, what is the optimal level of production? So let's go on to part B. I'm going to leave the original problem up here so we still can refer back to it. In part B, the second question we are going to ask is, we would like to find the total profit function. Okay. So while we did not need that to determine the optimal level of production, we still may want to have a total profit function. Okay, so to find that total profit function, the thing that I know is that profit is revenue minus cost, which means that we want to come up with a formula for revenue and a formula for cost. So let's start with the revenue function. So for our revenue function, the information that we're given in the problem is that marginal revenue is 180 minus 2x. So we know that marginal revenue is 180 minus 2x. That's like saying r prime of x is equal to 180 minus 2x. So if we want to find the original revenue function, we want to find the antiderivative of 180 minus 2x. So our revenue function is the integral of 180 minus 2x dx. So the integral sign and the dx say find the antiderivative of the thing in the middle. Okay, so to find the antiderivative of a number is the number with an x tacked on. And then I write down the minus sign. And the antiderivative of 2x, well, I'm going to start by adding 1 to the power. So our power up here was 1. So we now have x squared. And I'm going to divide the number in front by the new power. And then I have a plus c at the end. Okay, so we have revenue is equal to 180x. 2 divided by 2 is 1. So we have 180x minus x squared plus c. Okay, now the thing is that if we really want to come up with this revenue function, we need to figure out what the correct value of C should be for this particular example. Okay. Now, this C at the end represents that the revenue function had some constant at the end, but we don't know what that is. So we need to figure out what that C value is for this particular revenue function. So we need to think about something else. And one thing that we know that is not written down anywhere in this problem is, well, ask yourself this. So ask yourself this question of, if I sell 0 units of a product, how much money am I going to make? Well, the answer is $0. So if we sell 0 units, we will have $0 in revenue. Remember, revenue is only the money being brought in. We're not thinking about costs at all. Okay, so we know that if we sell 0 units, then our revenue will be $0. And I can use this piece of information to calculate what C should be equal to. Okay, so I know that if I plug in 0, meaning 0 units, I have 180 times 0, that's 0 units, minus 0 squared, that's 0 units squared, plus C, that should be equal to $0. Okay, so once I plug all this stuff in, I can solve this equation for C. Now this is actually pretty easy to solve for C because I have a 0 here, a 0 here, and so what I end up getting is that C is equal to 0. So in this particular example, our constant for this particular revenue function is going to be 0. So our revenue function, Franklin says hi, our revenue function is 180x minus x squared, and our plus C is plus 0. So here is half of our profit function. All right, we're now ready to look at the other half of our profit function. Now, you might be thinking to yourself, wow, Diane, that was a lot of work to come up with C equals 0. I mean, why did we have to go through all this work right here? Well, it turns out that on revenue functions that are more straightforward, meaning ones that are just x's raised to powers, that our plus C is most of the time going to be 0. That changes once we start having some more complicated functions. So after we look at section 12.2 and 12.3, our functions are going to be getting more complicated. And then that plus C may or may not be a 0 all the time. Okay, so let's go on to our cost function. So we have our revenue function, and now we want to find the cost function. And the information that we're given is that we are told that the marginal cost is 6x plus 60. So marginal cost is 6x plus 60, and another word for marginal cost is derivative of cost. So if I want to find the original cost function, I want to take the antiderivative of 6x plus 60. Okay, so to take the antiderivative of 6x, I'm going to add 1 to the power, so I have x squared, and I'll divide the number in front by the new power. So I have 6 over 2 times x squared plus my antiderivative of a number, in this case 60, will be 60x. And then I have plus some arbitrary constant at the end. So here is our total cost function. Before we figure out this plus C for our cost function, I want to pause here and make an observation and a warning. For 2/3 of this semester, you have spent your time calculating derivatives. And now I'm asking you to think about this backward process of finding an antiderivative. So in your head, you've been taking so many derivatives that you might look at a number, like say 60 sitting by itself, and say, oh, well, I know what the derivative of 60 is. It's 0, and I can just ignore it because it's just a number. That's a derivative. Make sure when you are doing this process of finding an antiderivative that you think carefully about what you're doing, because if you're tired or you're not thinking carefully about what you're doing, it's really easy to slip into accidentally taking a derivative when what you mean to do is take an antiderivative. So keep that in mind when you're working on the material in Chapter 12 and Chapter 13. Okay, so back to our problem. We have our cost function is 6 over 2, so that's the same as 3. So we have 3x squared plus 60x plus c. And we're almost done with the cost function, except that I need to figure out what that plus c is going to be at the end for our cost function. And the way that we figure out what that constant is going to be for the particular example that we have is I need one extra piece of information. Now, with the revenue function, that was not told to us. I just needed to know that if I sell 0 units, that the revenue will be $0. And I need to know that. I'm never going to be told that. On the other hand, when it comes to cost functions, you have to be given information about that because costs are different in every single example. So let's look at what we were given at the beginning. Blah, 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 blah. The last sentence says that the company's total cost of producing 10 items is $1,000. So what this says is that we are told that the cost of producing 10 items, so C of 10, is equal to $1,000. Okay. So I can use this piece of information to figure out what that plus C is going to be equal to. All right, so what this tells us, the cost of producing 10 items is $1,000, says that if I plug 10 in for x, 3 times 10 squared plus 60 times 10 plus c, that expression had better be equal to $1,000. Now, this is not as easy to solve as the last one over with revenue. We had 0 plugged in, so that was easy to deal with. Here we don't have 0. Instead, I need to do a little bit more math. So we have 1,000 is equal to 300 plus 600 plus c. So 1,000 is 900 plus c, and I can subtract the 900 from both sides. And we get that c is equal to 100. Okay, so that tells me that our cost function, c of x, is equal to 3x squared plus 60x plus c, which in our case is 100. Okay. Now, just as a comment on this, it happens that 1,000 divided by 10 is equal to 100. That is an utter coincidence. So do not think that you can just take the 1,000 divided by 10 to get your plus c. That happened to be the case this time, but that is not always true, so don't do that. Okay. This 100 at the end, on the other hand, is our fixed costs, because if I plug in 0 for x, in other words, if we produce 0 units, we still have a cost incurred of $100. So an observation is that the fixed costs are $100 because when I plug in 0 into my function, my output is 100. Okay, so we are now ready to actually answer part B. In part B, we're asked to find the total profit function, and we've now figured out our revenue function and our cost function. So profit is revenue minus cost, Our revenue function is 180 minus x squared, 180x minus x squared. And our cost function is 3x squared plus 60x plus 100. So totally fine profit function, but maybe I will try and simplify this a little bit. And so that means I'm going to be distributing this negative sign. So we have 180x minus x squared. Remember, I need those parentheses around the cost function because it's minus the whole cost function, which means when I simplify, I need to distribute the negative. So we have minus 3x squared minus 60x minus 100. Okay, so our last step here, I can combine the x squared. So we have negative 4x squared. 180x minus 60x is plus 120x, and then minus 100. And so we have found our profit function. Okay, so our final part to this problem is we would now that we have our profit function, we would like to know what is the profit if our company achieves its optimal production level. So part C, we are going to ask, what is the profit or possible loss at the optimal level of production? Now, we saw in part A that the optimal level of production occurs when we produce and sell, or our company produces and sells 15 units or 15 items. And so we can plug that 15 into our profit function. And so when I do that, I have P of 15 is equal to negative 4 times 15 squared plus 120 times 15 minus 100. And when I typed that into my calculator, at least when I did, I came up with a value of 800. And so what that tells me is that the max profit for this company is achieved when 15 units are produced and sold and the max profit is $800. Now, that's not a very impressive number right there. So this is not going to be a company that's going to do that well if their maximum possible profit is $800. But hopefully you get the idea. All right, now before we wrap up this lecture here, one way to come up with this profit value of 800 is by plugging our x value into the profit function that we came up with. Alternatively, you can use your graphing calculator. So I'm going to bring you over here to take a look at, I have a computer version of our graphing calculator. And so what I've done is I have typed in the function that we are looking at, negative 4x squared plus 120x minus 100. And if I go to Zoom and I scroll down to Zoom Standard, and maybe hit enter, then I get a really strange looking graph, but that's okay. But what I want to think about is what is a reasonable graph? And what we saw was that our maximum occurs when x is equal to 15. So I definitely want to have a window that will have an X value of 15 included in that window. And since it's going to be the top of the hill, maybe somewhere in the middle, so I'll make sure that my X value, the X maximum, is 30. Oh, hi, Franklin. Come here. And as far as an X minimum goes, well, X represents the number of units produced and sold, so it does not make sense to talk about a negative number of units. So let's start this X minimum at 0. So once I've plugged in the X minimum and the X maximum, then I can go to Zoom and scroll down to Zoom Fit. Okay, remember that Zoom Fit will figure out the Y values for us as long as we tell it what the X values are ahead of time. So I hit Zoom Fit, and here is our graph. So this is our graph of the profit function. And if I click on Trace, and I type in, well, it happened to start at 15, and I type in 15 and hit Enter, the X value is 15, the Y, which represents profit, is 800. All right, so go ahead and show me again. So that's all for today. Have a great night, and we'll see you soon.